So, um, Today I'm going to talk about the intersection of AI and health data science, which will be divided into two parts. And I'll try to keep it a little interactive as well. Not too interactive, but there'll be some interactive components. So, part one, I'll talk about my research in consumer digital healthcare and in the process, sort of outline some general problems for the field of digital health, and in particular, digital health using consumer devices like smartphones and wearables and websites and things like that, as opposed to like electronic health records or radiology or that kind of healthcare, digital healthcare. And then in part two, I'll zoom out and be a little bit more broad and talk about some relevant human-centered AI methods that are very useful for healthcare. So I'll teach you a little bit about some of the state-of-the-art AI methods for privacy, as well as some state-of-the-art methods for fairness and bias mitigation, as well as some state-of-the-art methods for explainability. So that's a lot of content, but we'll see how far we get. And if we don't get to all of it, then that means that we had a very interactive session, which is great. So without further ado, let's start with the first part on my research. And so my research, if you don't know, is in consumer digital healthcare. And so um, that means working with data from smartphones or wearables or custom consumer devices like blood pressure monitors that are integrated to Bluetooth, or continuous glucose monitors for people with type 1 or type 2 diabetes, or the Oura Ring, or social media, or other types of patient generated health data. And so there's a couple of problems when working with these types of data versus, let's say, a tabular data set that you could easily put into scikit-learn, for example. And so the first problem is that they are often used to predict highly subjective, heterogeneous, and nuanced health outcomes. Things like in mental health or other patient reported outcomes. They are inherently subjective, and which makes it very challenging versus predicting something like they have diabetes or not, because that's just, you do that measurement and you know if their glucose level qualifies them for a diabetes diagnosis. But for things in psychiatry and behavioral sciences, you can't do it like that. And so what I propose, and what I'll talk a little bit about today, is human in the loop AI as a solution for this inherent subjectivity and heterogeneity of the health outcomes. Another central challenge in working with consumer digital health data streams is that this first problem on the left, that's like the label, the why, the thing we're trying to predict. That's challenging. But also the X, the input to the model, tend to be very noisy, and importantly tend to drastically vary between people, between subjects. So for person A, they're going to have different patterns when they're using their smartphone versus person B. Now, that also introduces a lot of challenges. So what I propose to do to handle this type of issue in consumer digital health is personalized deep learning, often with the aid of self-supervised learning, so that we can, for example, learn to predict a repeat adverse health outcome again and again and again for that same person, like a blood pressure spike or a glucose spike or something like that. And so it doesn't work for diagnostics, but for therapeutics or interventions, it could actually work quite well. And so you'll see that in my lab, we tend to focus on our central problem of consumer health data. But we also work on methods, right? So we work on human in the loop AI and personalized deep learning in order to solve these fundamental problems that are largely specific to working with consumer health data streams. I mean, some of these problems happen in other types of data, but not as much. A lot of other places in healthcare, it's the data are much more clean. And so I'm going to talk about both in this talk, and I'm going to start on the human in the loop AI side of things. So I'm going to talk about the human in the loop AI side of things in the context of predicting autism in pediatric populations. So if you're not familiar with autism, 1 in 40 children in the United States are autistic, and autism is characterized by a wide range of behavioral characteristics, such as lack of eye contact, trouble with social responsiveness, and a bunch of other characteristics. And so when you hear people talk about autism, you've probably heard it referred to as a spectrum, and where anyone with autism falls somewhere on this 1D spectrum. And that's actually an incredibly misleading way of conceptualizing autism, because actually the literature supports that autism is many different spectra. So for example, a spectrum of emotional sensitivity, a spectrum of motor skills, etc. And what makes autism particularly challenging to study from a scientific standpoint is one of those challenges that I talked about at the beginning, where you could have one person with autism who is at the top of the emotional sensitivity spectrum and on the bottom of the motor skills spectrum. And by top and bottom, I mean visually, according to this picture. And then you could have another person with autism who is low on the emotional sensitivity scale and high on the motor skills scale. And then you could have another person who doesn't have autism, who is low on the emotional sensitivity scale and also high on the motor skills scale. And so that makes it quite challenging due to all of the variability within autism and also outside of autism. And so this challenging diagnostic phenotype of autism has led to a challenge in the diagnostic process for autism, where there's currently a waiting time for the current standard of care that exceeds 18 months on average in the United States, and often longer in other places, like in rural areas. For example, some islands in Hawaii that are not on Oahu, outside of Oahu. And unfortunately, this leads to systemic discrimination of underserved and marginalized populations. But fortunately, I think that digital diagnostics and this whole field of consumer digital health can help this problem, where if we can deliver screening or diagnostic services through devices that people already have. Almost everyone has a smartphone in the US these days, and it's continuing to grow. If we can deliver care, and in this case, a diagnosis through ubiquitous devices that everyone has, then we can really make a difference, importantly, in an affordable, scalable, and accessible way that psychiatry often isn't today. So to understand how the data science part of this works, we first have to do something that's actually always important in as a data scientist. Is if you're doing data science for X, it doesn't have to be in healthcare. It could be in any science area or social science or law or business or whatever. You gotta understand the domain and the data you're working with before you try to build, throw every scikit-learn model at it, because for many reasons. And so let me explain to you a little bit about the diagnostic process for both autism and also throughout all of psychiatry. The diagnostic process roughly looks like this. So when a clinician is evaluating a child for autism, they're evaluating the child with respect to several behavioral characteristics. And they're filling out a diagnostic questionnaire. So, these psychiatrists, clinicians, what they do is evaluate the child's behavior and rate each behavior on what the fancy term is a categorical ordinal scale, fancy way to say 0, 1, 2, 3 scale. And basically, where 0 might correspond to never doing the behavior, and 3 would correspond to always doing the behavior. And so, for example, the clinician might evaluate the child's facial emotion expression and rate the child as a 2, which might correspond to often emotes during conversation, as opposed to a 0, which might be never emotes during conversation, and a 3, which might equate to always emotes during conversation. So 2, somewhere in the middle, but closer to always emoting. And so that clinician would then record a 2 on the score sheet. The clinician then does that for all the other things on the diagnostic questionnaire and records the 0, 1, 2, 3. And after that, to get a final diagnosis, what they do is sum up these numbers. And it's literally an if-else statement. Fancy word for that is rule-based algorithm. But you sum up all those numbers, and if that sum exceeds a certain threshold, then a diagnosis is provided. And if that sum does not go past the threshold, then the child does not receive a diagnosis. So that threshold might, for example, be 20. And if the sum is greater than 20, then a diagnosis is provided. If it's less than 20, then no diagnosis. And so the data that we largely work with in the lab are tabular. I mean, at least one of the initial data sets we worked with, and me and many others, where the rows of the data set are each child and the columns are the clinician filled score sheet values from 0 to 3 and the corresponding diagnosis, which, you could just, technically need that. You could just add up these numbers and you get the diagnosis. And so what we wanted to do was to build a machine learning model that can predict the diagnosis given the inputs to the model. And then we can do things like feature selection, which is a data science technique, which is how do we algorithmically determine which of the inputs to a machine learning model are most predictive of the outcome, to algorithmically deprioritize features that are not predictive of autism, such as eating frequency, which doesn't appear in the score sheet, but if it did, it would certainly be deprioritized. And on the other hand, prioritize those features that are highly predictive of autism, like facial emotion expression, which is highly predictive. And so what we would like to do then is build machine learning models that take these top ranked features and extract those, quantify those features using computer vision, and then take those quantifications and put them into the diagnostic algorithm. The problem, though, is that a lot of these questions on the score sheet go well beyond what computer vision models can do today. So, for example, in one of these score sheets, one of the questions is, does the child enjoy participating in social games and interactions? So I don't know about you, but even when I interact with ChatGPT, which is an LLM model, it can't answer these types of questions. Like if I gave it a transcript of someone talking, I was like, does this person appear to enjoy participating in social games interactions? Can't do it right now. That's not to say you can't do it well. It hallucinates like crazy when you have it do something like that, even with the 4.0 and the new preview one. Now, of course, that's not to say that in 5 years, I'm pretty sure they're going to figure that out. But in the meantime, it's just impossible to use these models. And then, that's from a technical perspective. But the other perspective we have to have here is like, what are clinicians and what are practicing medical facilities willing to put in their facility, even if a an AI model could do this, where they could extract whether the child enjoys participating in social games and interactions, and then do that for a bunch of other behaviors and do it perfectly, and then put those 0, 1, 2, 3s into the classification model. Would hospitals allow that? Would people trust those AI models? Not entirely clear that even if it was technically possible that patients would trust it, that doctors would be willing to adapt it. And so, anyways, we're not even there yet because the AI models can't even do it yet. But I'm pretty sure that eventually they'll be able to do it. And I have a feeling that even then, doctors will still want to have some sort of evaluation. So, what I propose then is back to this human in the loop AI way of looking at things, where we don't just purely put in a deep learning model to do this classification, but we have a human work together with an AI model in order to arrive at a diagnosis. And we could explore, who is that human? Is that human a clinician? Is it a nurse? Is it another professional healthcare worker that's not a doctor or a nurse? There's many other people in the healthcare field besides those two professions. And so is it a speech and language specialist? Is it, and then even beyond there, could it be someone like a special education instructor or teacher, or a professor, or parents of other people who have developmental delays, or things like this? And so there's this efficiency standpoint. And then what are we using the classification for? Is it going to be an official diagnosis, or is it a screening tool that's meant to triage people and maybe tell them they're good, they don't need to see anyone else, but if it detects something, direct them to the right person? So there's all these questions of how are these AI models actually used in the real world, that are very interesting and that I plan to study in the future. But today I'm going to focus just on the pure technical standpoint of how can we get these human in the loop systems working. And so one study that I ran back a long time ago now, back in my PhD, was to explore what having crowd workers on Amazon Mechanical Turk do these ratings. I chose MTurk because you could get a large population of people, and then you can kind of filter out and see who is good from the crowd and compare different workers. So it was very interesting from that standpoint. And basically have those people go on these crowdsourcing platforms, watch short home videos of a child in question who may or may not have a diagnosis of autism, and have the crowd workers answer a series of multiple choice questions about the video that they're watching, where the answers to those multiple choice questions correspond exactly 1-to-1 correspondence to those 0, 1, 2, 3 rating scales I was talking about earlier. So basically, we have the crowd workers do those 0, 1, 2, 3 rating scales. And, you don't necessarily have to be an expert to watch the video and say, is the child repeating the last statement made by the caregiver? You could probably just watch it and understand whether that's happening. And so, but there's other questions that are a little bit more challenging, like the enjoying participating in social games and interactions. Well, maybe some people are good at identifying that and other people aren't. And that's actually what the study that I ran back in the day showed. And so what I did was have these crowd workers answer these questions. And as they answered the questions, it was generating those 0, 1, 2, 3 answers that then could go as input into the behavioral feature vector that is basically the input into a simple AI model that can give us the final diagnosis. So the human in the loop watches the video, and one technical way of looking at this is they convert the high dimensional complex feature space of the video to a low dimensional, easy to understand feature space, like the 0, 1, 2, 3 vector, and feed that vector into a machine learning model that can make the final diagnosis. Well, how do we get this gold standard classifier? Well, I already told you we have these data sets of clinician filled um, questionnaires. And so we can take those and train the gold standard model and then feed in the crowd responses into that gold standard model. And then we could have each crowd worker watch a bunch of videos, some of which are of a child who's diagnosed with autism and others that are not, and then go through this whole process. What is the AI model output? And we could compare that to the true values and essentially evaluate workers. And I did this and looked at all these different ways of quantifying who's a good worker and who's not. It's kind of interesting, like social sciencey, but machine learning still, but for medicine. So very interdisciplinary. And then um, once selecting these top workers, then having them watch a separate set of videos for a test set, essentially, and seeing how they perform. And so we did this, and this was the performance at first. So for one machine learning model, trained with 5 features, it got an AUROC of 0.99, and another one trained with 10 subset of features got an AUROC of point, also close to 0.99. So my question for you is, and this is the first interactive component where I think we could just have you type ideas in the chat. So this performance looks really, really good, right? Like almost too good to be true. And so here's a lesson. Oh man, I kind of gave away the answer, but hopefully you didn't see that. Yeah, what makes me suspicious, and every time I have a student now come to me and tell me, hey, I got 99% accuracy and 99% precision recall on whatever problem, it doesn't matter what the problem is. My first question is, what went wrong? Because I don't believe it's too good to be true. This is too hard of a problem predicting autism with AI. How the heck are we getting 99% AUROC? Something is fishy here. So of course the first thing I did was go back and debug everything and make sure that there's nothing wrong with the code or anything like that. So nothing like that. But can anyone tell me, okay, we're getting 99%, but like this is a very challenging problem. Why are we getting 99%? So any ideas that you could put in the chat about how can we more thoroughly, putting on your data scientist hat, evaluate the model and evaluate the data to see whether the performance is actually this good or if something else is going on. Okay, so we have a comment in the chat, data leakage of some sort. That's a great comment. So for those who don't know, data leakage means that you essentially trained with the same videos as those used in the test set. That was not the case here, but that's a great thought. I'll always look for data leakage. You never want your training data to also appear in the test data. Small sample size. So that is true. Yeah, so small sample size. Our sample size here was 50 videos in the test set, 25 autism, 25 neurotypical, which is pretty, in a training set, of course, much larger, but that's a pretty small test set. So that is part of it. Yes, but there's something more to it because 50 is still enough to where, yeah, if you're getting all 50 correct, something's up. Easy controls. Okay. I like that, Santiago. So yes, that was exactly the issue where, um, although not controls, it would be easy subject, easy individuals with autism. So what we thought was like maybe these videos of children who are diagnosed with autism are like very, very clearly autistic, and the videos of children without autism are very, very clearly not autistic. And so what we found is we recruited professional clinicians who are licensed to diagnose to watch the videos and provide something called a clinical global impression rating, fancy way of saying 1 through 7. another categorical ordinal scale, 1, 2, 3, 4, 5, 6, 7, where 7 corresponds to severe, whatever the condition is, and 1 corresponds to no, whatever the condition is. This could be anything in psychiatry. And so we had clinicians watch this, and we see that out of those, the videos that are of children diagnosed with autism, they tended to skew heavily towards the like severe side of things. And so, yeah, it did really well, but it was an easy data set. And so this kind of gets to an important issue in all of data science, which is you could report really good performances, but you know, it's how hard was your data set to classify. So for some paper, I've seen papers published in like Nature Medicine or like these top journals that get like 70% accuracy, but it was such a hard problem that getting 70% accuracy was very impressive. And for in this, we could argue, well, okay, well, it's kind of an easy data set to classify. But anyways, because it was easy, it allowed us to look into some more interesting sub-analyses. So one analysis we ran was looking into privacy. So, okay, we have a model that performs pretty well at baseline. What happens, some issues here, like if we're putting videos of children online for crowd workers to watch, or anyway, anything in human in the loop, like who are the humans in the loop, and is patient privacy is gonna be a very important consideration. If it's a clinician, that's one thing. Anyone else, let's say it's parents of children with developmental delays, well, who are those parents? Maybe we don't want to share their raw video. So as a first pass at this question, we looked at applying some privacy preserving modifications, such as boxing out the face and pitch shifting the audio. So it kind of sounds like those documentaries where like the voice is really deep and it's usually like a drug dealer or something. So it's kind of weird for the kids to sound like that. But anyways, it made it anonymous. And so we looked at, okay, if we just do the face box, we just do the pitch shift, and then we do both, how does that affect performance? And what we found is that the AUROC went down. And these are technically area under the precision recall curve, which is slightly different than ROC curves, but similar idea. And it went down with each privacy technique. And when you applied both, it went down even further. But if we break it down even more, we could change, because we're using logistic regression, we could change the threshold, play around with the threshold such that we can get high sensitivity. Sensitivity is a medical word for recall, as in precision recall. So we could get high sensitivity and lower specificity. Specificity is different than precision, but we also had lower precision. Specificity is just more of a medical relevant to diagnostic evaluation metric. But think of this, I know y'all are probably more familiar with precision recall, so think of this as high recall, low precision. Can anyone tell me, maybe in the chat, is why would playing around with the threshold, so the accuracy gets a little lower, but the sensitivity is really good, but the specificity goes down, why would we want that in a healthcare AI setting, a diagnostic AI setting?
Because you want to be absolutely sure.
Yeah, we want to be absolutely sure that if so that's actually that's the opposite. So that would be high specificity, means if we say that they have autism, they definitely have autism. This one is almost the opposite, where we're saying if we're not missing anyone with autism, we might classify some people who shouldn't have a diagnosis as autistic, but what type of medical application would that type of model be useful for? Okay, so in the chat we have, if you believe false negatives are more problematic than false positives. So yeah, I mean, you could argue in this case that for a screening tool, um, if we miss someone with autism or with any health condition, um, you could argue whether autism is a health condition, but if you miss a diagnosis, then that's going to be more problematic than if you tell someone, hey, I think you should get a diagnosis, but but they don't actually get the diagnosis down the road, because what's the worst that'll happen in that case? Well, they have to make an extra doctor's visit, but that's not the end of the world. At least you're catching everyone who should get a diagnosis, even if you're getting some people who don't need the diagnosis, but at least you're not missing anyone. Can anyone tell me who would be a stakeholder in healthcare that would want the opposite? So what was said before, where you're absolutely sure that they should have a diagnosis, even if you miss a few people? Can anyone think of any stakeholder in the healthcare system? So I hear cancer diagnosis. So cancer diagnosis is still, it could be any health condition. You probably still want the higher recall because, yeah. So insurance company, that's exactly right. Because insurance companies, if you say it's, they have a diagnosis and they don't have the diagnosis, then that's a lot of money wasted by the insurance company. They don't want to waste money. So if you're working for a health insurance company, or actually any insurance company, they're going to really want your specificity to be high. And they don't really care too much about sensitivity. So it's very important to think beyond the numbers, and especially for models like logistic regression, where you can tune the threshold. When you go out and be a data scientist in the real world, how do you optimize your model? You don't have to have the decision threshold be 50%. You might move it to 0.7 or 0.3 based on the application. So this is why understanding the domain you're working in is critical to being a data scientist. You don't just throw things into scikit-learn. You think about how it's going to be used and adjust the models accordingly. So anyways, we looked at some other privacy preserving techniques like blurring and pixelation and whatnot. Can anyone think of, okay, let me go through these more slowly. So blurring, we just blur the image. Pixelation, we pixelate the image. Optical flow is traditionally an activity recognition feature representation, but it kind of anonymizes it as well. You just kind of see the outline of things moving. Anyone think of maybe more modern, sophisticated techniques? Perhaps using generative AI. Yeah, so deep fakes would be a good one. And so the challenge, of course, is to make it still realistic, and like it should still be doing the activity. So it's actually a challenge. People are thinking about this though. How do we alter the images to preserve privacy but not lose the relevant behaviors? It's a very, very challenging area. Not sure that people have solved it yet, but could be a very interesting PhD thesis. So anyways, that's the first area of human in the loop AI. And we just touched upon one example of humans working together with AI models and some of the other issues with diagnostic AI. So now I want to turn to the personalized deep learning side of things. So as a reminder, zooming back out, the other fundamental challenge in working with consumer health data streams is that the data are very noisy and drastically vary across people. So person A's data, smartphone data is going to look very different than person B's smartphone data. So what I propose for this is personalized deep learning, where instead of the status quo, if we build one AI model and we give it to everyone, instead we build a separate AI model per person and use self-supervised learning to help us do that. And this doesn't necessarily work for diagnostics, but for areas like therapies or interventions where we want to detect something that happens again and again for a person, then this type of paradigm might make a lot of sense. So here's the idea, pretty simple, different AI model per person. And so more specifically, I'm interested in looking at wearable data, from a Fitbit or Apple Watch, or there's some more sophisticated devices you can get now, like an Empatica E4, or I think it's called Embrace Plus now, or these types of devices, where we get longitudinal time series data of things like heart rate, SpO2, skin temperature, accelerometer, those types of signals over time. And then we also need to get many labels per person of whatever adverse health event we're interested in over time. So that health event might be a blood pressure spike, or it might be a blood glucose spike, or it might be stress, or it might be using drugs, or it might be a whole host of other things, but something that we want to be able to detect again and again and again, and then intervene digitally, for example, using an app. It's a whole area of research is AI-powered interventions. And so in order to make that work, we need the AI part to work. And I think these types of health events like stress or drug use or whatever, that's very, very, very subjective again. And it's very challenging to make a general purpose AI model for that kind of thing. Very, very challenging. So instead, though, we might hypothesize, well, for within a single person, whenever I personally get stressed, my heart rate does this and my skin temperature does this. It's probably different for this other person, but for me personally, when I get stressed, this happens to my biosignals. So therefore, I'm just going to train the AI model on just my data, but my data over a long period of time, thus giving me many data points to train on. And so we have a project at UH on doing this for substance use. We have another one doing this on stress-induced blood pressure spikes. And the challenge in both of these and many other related areas is that it's hard to get enough labels for deep learning, right? Or we're going to get like 10,000 labels from one person. That's not feasible. So what we can do instead is use this idea of self-supervised learning to learn from all of these passive data like heart rate and skin temperature and accelerometer that we don't need human labels from, where we just get that data just by the person wearing the watch. They don't have to do anything else, just wear the watch. And we can use this idea of self-supervised learning to basically learn that person's baseline biosignal patterns and then refine the model with just a few labels of the adverse health event that we actually care about. So this idea is actually very similar to how ChatGPT works. So maybe really quickly, by show of hands, who is familiar with how ChatGPT is trained? You could do the reaction show of hands. Okay, so couple people, but mostly no. All right, so here's what we're gonna do. I'm gonna go get a drink of water because I have a little cold. So I'll be back in 1 minute. But then when we come and we have a lot of things to discuss. So when I get back, we're going to talk a little bit about how ChatGPT was trained, and then we're going to talk about how that same type of training can also apply to learning from from biosignals from Fitbits and smartwatches. And so I'll be right back. We're waiting. Got my big glass of water. So yeah, so the way that ChatGPT was trained is actually pretty intuitive. And so we're going to talk about it at a very high level. So, what OpenAI did, and this is really the first step of training ChatGPT, was to collect as much data as they could from the internet. So, mining Wikipedia and text on websites and stuff like that, and to train a model called GPT, which is not ChatGPT, it's just GPT. What they did was they trained a deep learning model to predict, given a few words, what is the next word. So, auto-regressive modeling is the fancy term, but, just predicting what's the next word given the previous sets of words. So very simple, but very beautiful. And it's beautiful for two fundamental reasons. The first is that, well, if you can train a model to successfully predict what's the next word given the previous sequences of words, then you have a model that understands human language pretty well and could therefore be fine-tuned to do something like responding to prompts pretty easily, because it's starting off with already understanding human language. So it's not that far to go from that to responding to prompts. And on top of that, it's generating text, because you have 5 words, generate the 6th word. Now you have 6 words, generate the 7th. So it's very simple, and yet it's very powerful if you have enough data, which they do because it's all the text on the internet, and enough computing power to do it, which OpenAI does. And so that's the first reason it's beautiful. The second reason is that you don't need to do anything else. You don't need human labels, or in other words, you don't need this Y label that you have in supervised learning. You don't need humans to go and label all the text and say this text is this and that text is that. No, you just get the labels for free. Take any 10 words, make the first 9 words the input to the model and the 10th word the output. And so it's very simple to do. And so basically running that process into a fancy transformer deep learning model, they were able to get GPT. And then they took GPT and then they used some humans in the loop to refine it to get to ChatGPT. But just GPT by itself that foundation model is very powerful. And so bringing it now back to healthcare, what we're interested in doing is the same thing, but with biosignal data. So instead of predicting what's the next word given the previous sequences of words, instead we can predict what is the next portion of the biosignal given the previous portions of the biosignal. And these signals are really just 1D arrays, right? It's just a wave. And so it's actually even simpler than predicting text because it's not words, it's just a number. And so, there's many ways to do this. And now we can do this in a multimodal way where, for example, instead of predicting what's the next word for this signal, given the previous portions of this signal, we could predict what's the next portion of this signal given the previous portions of other signals. So like what's the next portion of the heart rate given the previous skin temperature and accelerometry data. And by doing that separately for each person, we get what we can think of as a personalized foundation model that understands the basics of how that person's biosignals change over time, just as they go about their day. And then, since we're starting off with a model that already understands that person's biosignals, it doesn't take too many labels anymore to get that towards predicting whatever adverse health events we want. Just like with, relatively speaking. So just like with GPT, how once you have GPT, a foundation model that understands how human language works, it doesn't take too many labels, relatively speaking, to get to Chat GPT. So we ran a few studies and found that the personalized models does better than the generalized models. And we also find that the marginal effect, the benefit of doing this improves, tends to go down when we have more labeled data. So this is really useful in settings where we don't have a lot of labeled data. When we have a lot of labeled data, it's not as useful. And we did some more analyses. But and we found that it does well in like predicting stress. Well, we also found, and this is very, very important to talk about in data science and in research in general, is that when do things not work and why did they not work? And especially when you would think that it would work, but it doesn't work. So it worked really well for a few data sets. And the thing about these data sets is that they were collected in the lab in very idealized, controlled settings. And so that's great. That means that all the participants are following the exact same procedure. But what we care about in consumer digital health is like having people go out in the real world and interacting and doing this in the messiness of the real world. And so the next data set that we looked at was a data set of nurses who were wearing a biosensing wearable during the beginning of the COVID-19 pandemic, during their work hours, and were asked to annotate their stress, label their stress throughout their work. And of course, this is a very stressful time for nurses, as you might imagine and or recall. So there were many problems with this data set, as you can imagine. So first of all, the nurses were stressed, so they didn't label their data consistently, both across nurses, different nurses labeled differently from each other, but also for the same nurse, even on the same day, they didn't label in the same way. So that, personalization could, in theory, help this first issue, right? If it's different across people, well, that's the whole point of doing personalization. But if even the same person is not being consistent with themselves, then personalization can't help you there. And so that, together with the noisy data and inconsistent labeling procedures, led to a very messy data set where essentially we did not see any improvement in the personalized models using self-supervised learning versus not. So you could say that's sad, but I actually think that's very exciting because it shows that there's so much more work to do in order to make this work in noisy, stressful, demanding real world settings rather than collected in the lab. And that brings us to a very important side of data science, which is, can we create human computer interaction innovations to collect the data well, even in these highly stressful situations? And so this has kind of led me to my next line of research on this side of things, which is to develop ways to make sure, AI-powered ways to make sure that the data coming in are still of high quality. And so one idea for doing that is to look at the AI model's confidence at any particular time and to, if the model is confident, so it makes a prediction and it predicts 99% stress. Well, okay, at 99% stress, the model's pretty confident that it's stress. So we don't need to bother asking the person whether they're stressed or not because the model's pretty sure. Later on, the model might predict stress, but 56%, where 50 would be random, 49 would technically be no stress. Anything above 50 is stress, anything below 50 is no stress. Typical binary classification. And so it might output 56%. And technically it's predicting stress, but it's like barely predicting stress. And it could have just been random chance that it's on that side of the 50% versus on the other side of 50%. So in that time point, it would be very useful to get another label from the person so that we could further make our model more confident. So that's an example of an AI powered human computer interaction innovation where we're changing the interaction based on the output of the AI model and reducing user burden, ideally. Another thing we're looking at is to gamify it a little bit and to just tell the user what the AI performance is at all times. Like, hey, the AI is at 70%, provide more labels to improve it, and seeing if that works, looking at combining these, and a whole bunch of other variations of this. So, in summary, I think that's all I want to talk about in terms of my research. So I talked to you about consumer health data streams. I talked about challenges with the labels and the challenges with the inputs to the model and some various ways to address both issues. So human in the loop AI to address the subjectivity of the conditions we're predicting, and personalized self-supervised deep learning to address the variability across people in things like digital interventions and therapies. So we just took a short break, so we won't do a short break anymore. But any questions about my research before we go into more general human-centered AI lessons? Hopefully there were some general lessons in my research as well. So to summarize, if you get really good performance, look into it more because it's probably if something's fishy, especially if it's a hard problem, and always look at different look into the data more and most importantly understand your domain very well because you don't just blindly apply scikit-learn. You will adjust the properties of the model based on the domain that you're trying to work in. All right, so question: how do we know which parameters are best to use for healthcare analysis? Um, so I could, at one end you could just do hyperparameter optimization, but I think it actually depends on the specific healthcare domain. So I wouldn't group all of healthcare analysis into one monolith. I would say that if you're, first of all, if you're doing computer vision versus natural language versus wearable biosignals, those are all very different. And then the specific health condition you're trying to predict, it's going to be a very different modeling procedure, including parameters, including hyperparameters, including even the way you evaluate the model. So, yeah, I can't answer that question generally. I think it's a different answer for every single problem that you're working on, both inside and outside of healthcare. Other questions? Yeah, again, for diagnosis, it differs based on modality, computer vision, NLP, wearables. The thing you're trying to diagnose, is it diabetes or etc.? And then who the stakeholder is. We talked about whether it's an insurance company versus someone trying to maximize the amount of people that they see for a screening tool. Yeah, it all depends. And we talked about some examples of different, I guess we didn't talk about parameters. We talked about hyperparameters like the decision threshold. But we talked about, different examples where you would want one end of that decision threshold versus the other. Well, good questions. If y'all have more, keep them coming. Um, so now let's quickly end with part two, which is talking about some general human-centered AI methods that happen to be useful in healthcare, but are also more broadly useful. So we already did our break. Um, so the first is in privacy. So as you can imagine, in healthcare, we care a lot about privacy. And so unfortunately, though, when we're developing AI models, there's this fundamental privacy accuracy trade-off that could happen where if we do that thing I was showing before where we box out the face, okay, we're giving more privacy to the patient, but the AI model performance goes down. So there's this inherent trade-off. And so quick poll, and we'll see if your answers to this change after I go over privacy. So where do y'all think is the right place to fall on the spectrum? And then you could type in comments in the chat. So I'll start on, what was the, oh, I didn't label this, but okay, we're going to say the left is privacy and the right is accuracy. So it matches the title. Who thinks that by reaction, we should be on the left side? So prioritizing privacy over accuracy. Okay. Who thinks that we should be on the right side? So prioritizing accuracy over privacy by all means. Okay, a couple people. Okay, who thinks we should be in the middle? Yeah, we could sacrifice a little bit of accuracy if it gives us privacy. Okay, a couple of reactions. Okay, a lot of reactions for that one. Okay, and that's usually what the answer ends up being, is so maybe I won't do this exercise anymore, but it's usually like you have to make some trade-offs and usually you want to be somewhere in the middle. And so let's talk a little bit about some privacy issues. So who's into hacking here? Just by show of hands, just like general hacking. Because did you know that you could also hack ML models? So this is beyond like your traditional like buffer overflow or SQL injection attack or like all those things you learn about in a computer security class. But instead, we can get information out of our machine learning model that we don't want general users of that machine learning model to know. So in healthcare, that could be, for example, we could get protected health information out of the model just by putting in the right inputs into the AI model and trying to basically get out whether my private training data is in the training data of the model, which could be an issue, right? Because if our, we might know that the model is trained very specifically on people who have income greater than $1 million. And so I don't know, I'm just making this up, a greater than $1 million, which is not a bad place to be. But so let's say that, okay, if you might know someone's income just by querying the model and seeing that they're in that training data, knowing that the training data was only trained on people who make more than $1 million. And so clearly an issue, more so an issue when the training data is not more than $1 million, but on populations where it would be sensitive to know their information. And so there's all these different ways of conducting what's called this membership inference attack, where we can figure out whether someone was in the data set or not. And, you could do things like adding what's called adversarial noise as well to change the output of the model, and which could be very much an issue. For example, in computer vision, if you add some noise to the image, you can now, perhaps make your face confuse the AI model to detect you as someone else. Or if you're a self-driving car, you could, change the stop sign a little bit so that self-driving cars stopping at the stop sign. Clearly be an issue. And there's many other ways to break it. So unfortunately, there's no complete defense of machine learning models, but there seems to be this cat and mouse game in privacy research where some researchers are creating new ways to break into ML models and writing about that, and others are creating new ways to fix those issues. And then some people are doing both at the same time. So they're creating the issue and then fixing their own issue. And so I want to talk about two of the most popular security techniques to preserve privacy in healthcare specifically. And so the first is called differential privacy, where it's the basic idea is to add noise to the training data set. And then the central question becomes, well, how much noise do we want to add? So basically, to make our data set differentially private, what we want to do is add just enough noise such that if we take the original data set and we add a second person's data, we don't necessarily know. If we have our data set and we add, for example, this person's data, and we conduct the analysis and get answer A, we should get an indistinguishable answer from if we had run that analysis on the data set without that person's data, because you don't want the addition of that person's data to drastically change the answer, is basically what it means. So there's math ways of defining that, but that's the basic idea. And there's many real world uses of differential privacy. So the US Census Bureau for the 2020 census used differential privacy. So added a little bit of noise to the data, but it added privacy. Apple uses differential privacy in their iOS and Mac OS for personal data, like search queries and the health data. Microsoft uses it for collecting data from Windows devices, and etc. So it's widely used even outside of healthcare. The second, different privacy preserving method I want to talk about that's popular in healthcare, but it also is used outside of healthcare, is called federated learning, where we want to basically learn from many different people's data. And so an example is Google uses federated learning to train, let's say it's trying to do autocomplete, for example. I think this is a real example. So they have an autocomplete model that predicts what's the next word that should be suggested. And it wants to create a generally good autocomplete model that's just does well for everyone, a global model. So it wants to train from everyone's text data. The problem is that people don't want their text data to be seen by Google or Apple. So what you can do is train a machine learning model separately on each device, so a local model, and then instead of sharing the data to the central server, you share the weights of the AI models. So if it's logistic regression, the M's and B's of the model, so, with the server, and then you average or do some other way of aggregating the weights to get your central global model. And then you're able to essentially learn from everyone's data without ever sharing the data. So a pretty clever technique, again, used in very real world settings like what I just described, but also used in healthcare, which is also a real world setting. Sorry, by real world, I meant like consumer devices and Apple and Microsoft and all that, but also used in healthcare for applications such as, well, we might have data from one hospital and data from another hospital, and we want to train the model on, learn from all the hospitals' data, but we don't want the data from the different hospitals to be shared between each other. So we can again do this federated learning so that we learn a model trained on each hospital, and then we could get a really good model that just aggregates all the weights from the individual hospitals. So I'll skip ahead on this, but quick ending note for the privacy part. Has anyone's answer changed in terms of whether you would prioritize privacy or accuracy or be in the middle? So only if your answer has changed, let us know, or otherwise I'll assume that your answer has not changed. Okay. So maybe there might be a delay, but it seems like people's answer hasn't changed. Okay, so I have a part on fairness and also a part on interpretability. I think that's a lot for today. So let's have a vote. Who wants a similar tutorial on algorithmic fairness? And then we'll have people vote shortly on if you prefer interpretability instead. Explainable AI. So vote if you prefer bias and fairness and ways to. Okay. Now, if you prefer explainable AI interpretability. Okay. So I think we got more votes for explainable AI. So I'm going to skip all the fairness stuff. All that's very important. There's a lot of interesting things here, but come to my class. Okay, so let's talk about the interpretability explainable AI. So a very important thing in healthcare is to understand why are the models making the predictions that they're making, or in other words, why did a model diagnose someone, for example? Like, did it diagnose someone because of some noise that it learned, or did it diagnose based on a very specific symptom that maybe the patient should know about and the doctor should know about? So explainability and interpretability are always very important, but particularly in healthcare. So one strategy, and I'm going to distinguish interpretability from explainability. So interpretability is this idea of using a machine learning model where we inherently understand why it's making the predictions just based on how the model works. So logistic or linear regression would be good examples of an inherently interpretable model, because these models are basically learning a linear equation. You have each input x1, x2, x3, and the weights of the model, so like the M1, M2, M3, the coefficients, tell us, in which direction, why is the output the way it is? So specifically in this example, let's say we're trying to predict longevity, how many years is someone going to live? And the inputs to the model are X1, which is the mean lifespan of the immediate family members over the past 100 years. X2 is the hours of exercise per day, average, and X3 is the average saturated fat per day. And so if we train the model on the training data and we see that the equation that it learns is the longevity is equal to 3 times the mean lifespan of family members plus 9 times the hour of exercise per day minus 16 times the saturated fat in grams per day, then that tells us that, okay, both the mean lifespan and the hours of exercise per day contribute towards a longer lifespan. So, a longer lifespan of your family members and lot more hours of exercise per day lead to more longer life because they have positive coefficients. And the saturated fat per day has a negative coefficient. So we know that, okay, the more saturated fat you eat per day, the less long you'll live. And so, and then even more detail, just not just looking at the coefficients, but looking at the value of those coefficients or the absolute value of the coefficients, we see that, okay, well, the hours of exercise per day seems to have a larger effect on longevity than the lifespan of the family members. And specifically, it has 3 times an effect because the coefficient is 9 versus 3. So we really, really understand if we're training linear or logistic regression, exactly why the model is making the predictions that it's making. Because we just look at the equation that was learned and we could learn everything that I just said. And so you could always use an inherently interpretable model. Do people think that neural networks are interpretable? So here's an example of a small neural network, not even deep learning. So yeah, I think that it's not interpretable because there's so many weights we can't even see what the weights are. Here's a attention-based model transformer, very not interpretable. Here's a large network used for brain understanding, very not interpretable. So the problem with interpretable models is that they're great. We totally understand exactly why it's making the prediction that it's making, but they're usually super simple, like linear logistic regression or decision trees would be another. And if the model becomes more complex, then it's no longer interpretable. But unfortunately, we often need complex models in order to reach good performance in AI. And so this gives us a conundrum. Well, we have this interpretability accuracy trade-off. Usually the more accurate models tend to be less interpretable. So that brings us to explainable AI, which we could think of as black box approaches that are the same approach regardless of the machine learning model that you're using underneath, give or take. And so if we're going to use deep learning, which is highly complex models that we are definitely not interpretable, then we can look at some explainable AI techniques that can still let us know at least a little bit about why the model is making the predictions that it's making. So there's a few black box explainability methods. And I won't go through all of them. I just want to give you a couple just to give you a flavor for it. And then I think I want to go to fairness as well, because I think we need to talk about fairness too. It's very important. Even if that means a little less time on explainability. So SHOP is a very, very popular explainable AI method and a feature selection method in general that can tell us which of the inputs to the model are most predictive of the output. And it's really interesting. It's based on a game theory idea where you essentially are so like very interesting because you're using economics for machine learning, but you're essentially modeling the features, the inputs to the model as players in a game where the game is maximizing performance of the model. And you're trying to see who in the team is contributing most towards winning the game. Or in other words, in this, that's the metaphor that it was originally created for. In the case of machine learning, it's which of the features are most predictive. And so you could actually create this equation to figure out the marginal contribution of each feature. It's very interesting. We don't need to go into the details of the equation for today, but just to let you know that that's a very interesting technique to study. And then for computer vision, a very popular method is called saliency maps, where we can literally look at the pixels that were most predictive of the outcome of interest. And so we could see that, okay, this AI model is predicting that this is a wolf. But when we look at why is it making those predictions, well, we see that it's the reason why is because of all the snow in the background. So it's basically learning that snow means wolf, which is an issue because that's not what it's supposed to be learning. Same in healthcare, right? You might have radiology images and it might be predicting, let's say it's skin lesions and it's predicting no cancer. And we look at the reason why, and we see that whenever the background in the image is a green painted wall, it predicts no cancer. It'll be very clear if that's the case if you create these saliency maps. And obviously that's, it might just happen that our training and test data happen to have a green background for the pictures of the hands that we're trying to classify. And so that's a very important, this happens all the time in machine learning where there's these little confounding factors that make you think that you're getting good performance, you're learning well, but really you put that model out into the real world and it does horribly. And saliency maps are one way to see that. So, okay, I want to end now by talking about fairness really quickly because it would be a shame to not talk about it. And very important in healthcare because we don't want our diagnostic or other AI models in healthcare to perform differently for different groups of people. And so sometimes you could argue that there would be an accuracy fairness trade-off, although it really comes down to definitions of accuracy and definitions of fairness. And by accuracy, I'm grouping sensitivity, specificity, precision recall, F1 score, AUROC, all as accuracy collectively. And for fairness, there's a similarly large number of evaluation metrics. So you can evaluate your AI models for F1 score, AUROC, MAE, all that stuff. But there's also additional metrics you could add if you want to measure how well is the model performing and is it consistently, is it performing across different groups? And so let us talk about some of these quantitative definitions. And this looks like a lot. It's actually very intuitive when we break it down. So one very, very common metric in algorithmic fairness is called equalized odds. And the definition of equalized odds, so this is a probability-based definition. So again, it's very intuitive. It's saying that we have equalized odds if the probability of predicting positive, where positive might be cancer, negative would be no cancer. So the probability that we predict cancer, for example, given that the true label is either cancer or no cancer, and the protected attribute is something, is equal to that same probability if the protected attribute was different. So for example, let's say, the probability of predicting cancer given that they have cancer and that they have a lighter skin tone should be equal to the probability that the model predicts cancer if the true label is cancer and they have a darker skin tone. And same thing for given that the label is no cancer. So that's called equalized odds. And we can measure that very specifically. We can measure the difference in these probabilities on the left and right hand side of this equation for different groups. And that gives us a metric called equalized odds difference that we can put as another way to evaluate our models. Another one is called equal opportunity. So the definition here is that the probability that we predict no cancer, given that the outcome is cancer, and it's a light skin tone should be equal to the probability that we predict no cancer, given that the true label is cancer and it's a darker skin tone. So um, a more specific definition than equalized odds. And I'll leave you with one more, even though there are many more definitions of fairness. So this is called demographic parity. Probably the simplest metric yet, where the probability of the model predicting cancer, given that the population has a light skin tone, should be equal to the probability of predicting cancer in the dark skin tone population, part of the test set. So we can measure these very specifically, and there's other quantitative definitions, and they all have different meanings, and some of them even have trade-offs with each other. And so it's very important to be aware of these different methods so that when you're evaluating your performances, you might have high F1 score, but maybe there's low equal opportunity. And so this happens a lot in healthcare. So, for example, there have been data sets published where it is the skin cancer example. You have much more examples of lighter skin tones than darker skin tones. And lo and behold, the model performs much better for the lighter skin tones than the darker skin tones. So, and we know that by using these evaluation metrics. And so there are a few solutions to mitigating these biases. And that is where the field of algorithmic fairness comes in. So I want to end today's workshop by briefly summarizing 3 algorithmic fairness approaches that span the different parts of the data science pipeline. So specifically the pre-processing, what we're calling in-processing, and then the post-processing side of things. So let's start with the pre-processing side, which is really data modification. So the simplest thing we can do is if we have so here circle is one group, square is another group, and triangle is a different group. I think of them as different demographic groups. If beforehand we have many more circles than squares and more squares than triangles, if we want to train our model fairly, we could just remove the circles and remove the squares so that we have the same number of data points per group. Well, what's the downside of that? Well, unfortunately, you're throwing away data. We never want to throw away data. So another thing you can do is the opposite, oversampling, where you can take the underrepresented groups and you could repeat data points from those groups. And then you have an equal number of data points per group. Well, what's the problem with that? Well, if you have repeated data points for a group, you have less diversity of data points within that group, and therefore the model's probably not going to be able to fit as well. It's probably going to be more likely to overfit still because you still don't have as much diversity within a particular demographic group. So this is still not fully solving the problem, even though it's getting better. This is out of order. Okay, so then the next approach we could do is kind of combining this oversampling approach with generative AI. So changing the data where we create essentially synthetic data points from the underrepresented groups in order to provide data augmentation for the underrepresented groups so that we both get more data points for the underrepresented groups, but still a diversity of data points through the generation. And so there's a lot of methods for doing this in computer vision and NLP, in like biology. There's something called fairness scans. Scans are, a way to create deepfakes. And you could have fairness scans that recreate data points, but across a spectrum of skin tones, for example. And so, if you're interested in this idea of generative AI, and now it would be diffusion models, you could combine that to create new data points in a fairness aware way so that you could get more data points for underrepresented groups synthetically. And that's a big field of research, actually. So for time, I'm going to skip the in processing, but now let's go to the post. Oh, sorry. I'm going to skip post processing, but let's go to in processing. And so this is the last technique I'll talk about today. So one thing we can do is change our loss function when we're optimizing our model. Traditionally, when we're evaluating, when we're training our models, we're saying we're minimizing the cross entropy loss or the mean squared error, the standard machine learning, like we're minimizing error essentially. And sometimes we could add regularization to penalize the model for doing unfavorable things like having too many model weights. But we could also regularize for other things. So fair regularization is essentially adding a regularization term to penalize the model not being fair. And essentially, we can define mathematically a particular definition of fairness. So I showed you a bunch of definitions of fairness. You can encode that mathematically using a differentiable convex term and put that in the loss function. And then you could say our full loss function is equal to whatever our loss function was before. So for example, for regression, mean squared error, but then we're adding penalization terms for bias. And so our goal is to minimize the loss, minimize the error. But if we're adding a term that gets higher when the model's more biased, we're going to try to optimize the model weights such that it minimizes that term as well. And then you could play around with how much do you weight the overall error versus the cross group error, differences in error, and you could get different effects on this trade-off of overall accuracy versus group accuracy. And that how much you weight it matters, because you could get fairness by just having the accuracy be 0 for everyone. That's one way of being fair. So you don't want to do that. So it's this balancing act. And so you could choose a hyperparameter, tune that hyperparameter, try different values for how much you weight the fairness terms over the general error terms. So anyway, I covered a lot of different methods today. I want to end with a workshop survey. So if you're in this workshop, go to go.hawaii.edu/lowercase a capital HK and provide your survey of the workshop. While you're navigating to that link, are there any final questions? I know we covered a lot of material, but the goal of today's workshop was not to make you thoroughly understand everything, but rather to expose you to the breadth of data science and AI methods that are applicable to healthcare, but also are applicable more broadly to data science that go beyond just building a good model. So, final questions?
This was great. Thank you for your time.
Okay. Thank you so much. Well, if there's nothing else, then have a great weekend and see y'all later.